Let's talk about scattering of light. It's a beautiful phenomenon occurring in nature, and everybody's witness to the colors that flourish, that make things beautiful around us. And scattering is the phenomenon uh, that's responsible for all that beauty that we are able to sense uh, with our eyes, with our feelings. So, if I talk about the electromagnetic energy, the electromagnetic energy which constitutes light, it can be partly absorbed, it or it can be wholly absorbed by the matter, in which the same energy is trapped within the atom. So these processes they do occur, and this light, this electromagnetic energy, can be absorbed partially or wholly, and 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 the atoms can absorb these things. They can absorb it wholly. They can absorb it partially, and there is this change in the state of the uh, electrons in the atoms, uh, and then when we have absorption, an atom after absorption of electromagnetic energy may re-emit energy, and this energy can be wholly or partly, or it may part with its own energy that it has, the electron, and take that additional energy and emit some more energy. It may absorb energy, say nu1, and it may emit energy h nu2, such that h nu2 is greater than h nu1. So so to say, the absorption or the emission of energy by the matter is in packets, or quantas, or we call them photons, and each quantum being characterized by just one parameter, and that parameter is this frequency. Nu of these electromagnetic oscillations. And the energy of each packet of the photon is h nu. And what is h? H is Planck's constant. Uh, and and to start with a very basic formalism of scattering, it comes with Rayleigh, and we call it Rayleigh scattering. And if we have some monochromatic beam of light, monochromatic, and we understand that monochromatic means single wavelength, and it's made to pass through a highly purified, transparent material. So it is passing by some pure transparent material. So let us assume that this is the transparent, highly purified transparent material, and and what happens is most of the light will pass through this transparent material, and only a small amount of it will be scattered in various directions of atoms and molecules lying in the path of this beam. And what Rayleigh did, he studied this phenomenon of scattering of light, and almost in the last century, and found that for many liquid scatterers, about 1,000 part of the incident light energy is scattered, and this light has the same wavelength as that of this monochromatic light that's interacting with them. However, the amount of energy scattered that scatters, it varies with the wavelength of the incident light. And using dimensional analysis, he derived an expression for the intensity of the intensity of scattered light. So what we have is we have a transparent beam material, highly purified, and what we do is we uh, we bombard it by the monochromatic light radiations, and most of the radiations pass. If I will redraw this kind of situation, so we have some point. At that point, uh, we have scattering. And now let me demonstrate this. Is what I do is I assume that we have a particle P, and and this particle has a volume V. In the path of the beam of light of wavelength lambda, which is basically a monochromatic light, and let us assume that Q is a point here, be some point at distance r from this point P, from this particle P. Now, if the size of the particle is small compared to the wavelength, then the secondary wavelengths from the different parts of the particle arrive at Q in the same phase. They arrive at Q in same phase. And hence the total amplitude that we receive at Q can be taken to be proportional to the volume of this particle. And the intensity of this Q is inversely proportional to the distance, to the square of distance PQ. As the intensity is proportional to the square of amplitude, it follows that this Q at Q Q is inversely proportional to R. Now, the amplitude is expected to depend on the wavelength of the incident light. Hence, the amplitude, which I assume in my case as A is amplitude. At the point Q, may be written as A equals A naught V lambda raised power x by R. And this A naught is the amplitude of the incident beam. So this is amplitude of incident beam. And writing the dimensions on both sides of this equation, okay, for A I will have L, for A naught I will have L, for V I will have L cube, for lambda I will have L raised power x by L. So this L and L can cancel. What I will have is L is equal to L raised power 3 plus x. And the power of this L is 1. I can find 3 plus x is equal to 1. So x will be equal to 1 minus 3, and this x will be equal to minus 2. So I can write down this equation for amplitude. And what will be that equation? That equation will look like, because I have got x equal to minus 2, so it will be A is equal to A naught V lambda raised power minus 2 by R. Okay, that should be the case. Now, intensity is directly proportional to the scale of amplitude. So what will be the intensity of the scattered light? This intensity will be proportional to A naught V by lambda raised power minus 2 whole square. So this intensity will be equal to, here we will have lambda raised power minus 4, and everything else can be boiled down to a constant k lambda raised power minus 4. So what can we see from this equation is that intensity is inversely proportional to the fourth power of wavelength. And when the particle size is small compared to the wavelength of the incident light, the intensity of the scattered beam is inversely proportional to the fourth power of wavelength. And the scattered radiation, that we have from this particle P, this is of the same wavelength as that of incident light wavelength. Now, this is what is called as Rayleigh scattering. So what we see here, that we have interaction of electromagnetic radiation with the particle, and this radiation is getting scattered from this point P. And the scattered beam has the same wavelength as that of the wavelength of the incident radiation. And the intensity of the scattered radiation is found to be inversely proportional to the fourth power of wavelength. This is what's called as Rayleigh scattering of the scattered light. It's inversely proportional to the fourth power of wavelength of the incident light. Now, provided, what's important here is that the size of the particles scattering light should be very small. Size of particles, it should be very, very small as compared to the wavelength of light, as compared to wavelength of light. So that's clear here, that the intensity of this scattered light, which we have obtained using dimensional analysis, that this intensity is inversely proportional to the fourth power of lambda, and this lambda is the wavelength of the light. And this clearly shows that for lambda large, lesser is this scattering. So if lambda is large, the scattered intensity is small. So now, if we consider the wavelength of red light, the wavelength of red is greater than that of wavelength of blue or violet. So we can say here that the intensity of blue light in the scattered, once you have the scattered light, the intensity of the blue light in scattered light is much more than the intensity of the red light. Okay, that should be the case. So this is possible only if we have the atmosphere. The atmosphere should be clean and it should be pollution free. So we can say here that just the appearance of the sky is an indicator of the fact that if the sky is blue, then we can say that there's no pollution in atmosphere. But if it is deviating from the blue color, that is directly an indicator of the fact that the pollution is there in the atmosphere. So now, when the Earth's atmosphere is polluted, suppose it's polluted now that I'm talking about, or it contains some dust or smoke particles. Now, when we apply the scattering, the Rayleigh criteria of scattering, which is basically I proportional to 1 by lambda 4, it's not valid there. This equation is not valid when we have dust particles, when we have smoke particles in the atmosphere. Now, in this case, what happens is the size of the dust or the smoke particle, or even the water molecules in the atmosphere, is large. and as compared to the wavelength of the incident light. So, in other words, what should I say is that the size of the most of the scatterers in Earth's atmosphere is large as compared to the wavelength of the incident light that is falling on these particles, wherefrom we get this scattered light. So, these scatterers, which are large in size, they absorb most of the light, and they re-emit less light, and moreover, the scatterers of large size, what they do is they scatter all wavelengths of light almost equally. Therefore, in this case, when you have polluted atmosphere, in this case the sky will look grayish. It will look grayish. Now, to be precise here is that when the white light falls from the sun, it enters the atmosphere of the earth. When it enters the atmosphere of the earth, the scattering of different colors takes place due to the interaction with a large number of very small particles that are present in the earth's atmosphere. And what happens here is that the wavelength of the blue light is much smaller than that of red light. Therefore, the intensity of the blue light scattered is much more than that of the red light. So blue is very large than that of I red, in accordance with the equation Rayleigh criteria. Thus, the blue, this is the basis for color to appear as blue. That's why we have a blue sky. And due to this fact, this sky appears blue. Now, the sky will appear black in the absence of atmosphere. So if we don't have atmosphere, if there is absence of atmosphere, in this case, no color is scattered under these circumstances. And what will be so quite significant here is that the twinkling of stars will be visible in the daytime, because there is no scattering in the absence of Earth's atmosphere. We can see stars during the daytime. And sunlight would be visible only if we look directly at the sun. So it will be visible to us only when we look towards the sun. So we can understand the beauty of scattering that Almighty has provided to everyone, and how this whole universe of the planet Earth, it glitters, and it glitters by virtue of this scattering of light, and we have beautiful sky. And at the same time, if we talk about the sunset time or sunrise time, the sun and its surroundings, if we look towards the sun during the sunset or sunrise, what it appears is red. We are able to see the reddish color surrounding the sun. And the light from the sun at the at the sunset or at the sunrise, it has to travel larger distances through the Earth's atmosphere to reach our eyes. So this light is deprived of blue color. Why it's because due to large scattering of the blue color is scattered a lot by the particles or the scatterers that will come, that will face the light, and only rich in red color wavelengths are able to reach our eye. Therefore, the sun appears reddish at the sunset or sunrise. So this is how Rayleigh criteria can be used to understand the natural phenomenon, like the blue color of sky and the red color of the surrounding atmosphere of the sun during sunset and sunrise. Now, what about clouds? I mean, when there are clouds, I mean, the clouds, what they do is they are made of particles, and they may contain some dust particles and water droplets. So talking about clouds here, so these clouds are made of dust particles, or they can be water droplets, and their size is very large as compared to the wavelength of the incident light from the sun. So their size is large, okay, as compared to the lambda that's coming from sun. So what happens here? The Rayleigh criteria, or the Rayleigh law of scattering, is not applicable in this case. It's not applicable because of the size of the dust particles and the water droplets in this case. So all colors are scattered equally through these clouds. Hence, the light which we receive through the clouds has all the colors of light in it. And as a result of this, we receive almost white light because it contains the components of all formats of light.